Hello and welcome to for Intuition. So, our problem for the day, do 3 unique non-collinear points define a circle? Before we head on any further, let's just define what our terms mean here. So, we got the terms unique and non-collinear. So, let's put them down here. Definitions. Unique and non-collinear. So unique, what that means, I'll show that by both like a true example and a false example. So if we have 3 unique points, we have 3 points that have different positions. So in this these 3 white dots, maybe let's make them different colors. 3 dark blue dots. They're different positions, they are unique. However, if we had 1, 2, and 3rd point on top of the other point, then they're not unique in that they have at least 2 of them share the same position. So we could have had it like this, where only 2 share the same position, or for some reason I have 3 points but I'm just putting them all on the same exact spot. Right, so that's not unique, sadly. I'm sorry, pal. Okay. And then non-collinear, you can guess it means not collinear, okay? And you'd be right. What does collinear mean? Collinear, so in this case, this is our false example because we want it to be the opposite of collinear. Collinear means that you can draw a line through all 3 points. So here, these 3 points are collinear. 2 points will always be collinear, 3 are not necessarily collinear. So for example, this, no matter what, you can't make one line that goes through all of them. That being said, 3 points are always coplanar. And this is relevant to like actually our proof for the day. So I'll just put a quick little thing here, because coplanar just means you, like a plane, you have, it's like 2 directions, and then you can just draw those 2 directions from the points. So they are always going to lie on a plane, right? Because you only need 2 directions to cover them, and a plane includes 2 directions only. So they're always coplanar, but they are not necessarily collinear. Cool. So now we got definitions out the way. Let's now try to approach our problem visually, then we're going to try looking at it algebraically. So we're going to start off with 2 of our points, points 1 and points 2. The ones that we have right here. And let's ask ourselves, where can the center of the circle be if we just have those 2 points? Well, for our center of the circle to be anywhere, it has to be at an equal distance from those 2 points. Because pretty much, just to clarify, what we're looking for here is for 3 points to lie on our circle. So let's say these are our 3 points. And this is our circle. They're all on the circumference of our circle, right? So for them to be on the circumference of the circle, they have to be at the same radius or same distance, right, from the center of the circle. So looking at our points 1 and 2, what are some positions that are at equal distance between the 2? Well, one such position is smack in the center. Perfect. Okay. So smack in the center, we know it could be here, because we got some sort of distance x, we'll call it, and in total, give x in both directions, right, from the center. Okay, and now what if we were to go a little bit up? Would that work? It should, because here. We got some distance y. This distance y would be shared between points 1 and 2. And we know that this distance would then be the same. We know this from our dear friend Pythagoras. A name that's probably either given you nightmares or just heard it so many times. From Pythagoras' theorem, we know a squared plus b squared equals c squared, where b and a are the legs of a right angle triangle and c is the hypotenuse, right? So in this case, a is a horizontal position. It's going to be your x squared. A vertical y squared equals r squared. Right, in this case, we got the same x and we got the same y, right? So that means everywhere we go, like assuming this is like a right angle, if we go up, go down, all those points along this infinite line are viable centers of our circle. Okay, that's good. Can it be somewhere else? Maybe like here? I'll give you a few seconds to think about that, and now I'll say, no, it doesn't work. Because here we have the same y, right? They have the same vertical distance, but now they have different horizontal distances. So maybe I shouldn't put it right above. Let's put it like here, just to make it more general. You got the some distance here from point 1 and some larger distance here from point 2, right? And you got the same vertical. So you got same vertical but different horizontal. And so they're not going to be necessarily, well, they won't be equal. Maybe just to write it out to make it, let's attach maybe some numbers to this. This 2, this could be 1, this could be 5. So 5 squared plus 1 squared, plus 2 squared would not be equal to 1 squared plus 2 squared, right? This being our value y, and these being our different x values, right? Okay. So it's gonna just be along this green line. Let's now introduce our third point and do something similar. We're gonna make this is a line that goes right through them. I'm gonna apply the same logic here. It's just gonna be a little bit rotated. So we're gonna take a point right in the center. We know this point for sure can be the center of the circle if we just had points 2 and 3. And then we're gonna go up at 90 degrees. So we have some distance, oh, so ugly, some distance x hat, so it's going to be different than x, have to be the same because we're not giving point 3 any particular placement. We've got some horizontal distance that is the same from the center point, and then we're going to get some shared vertical quote-unquote distance that we will call y hat, and it can go in either direction. But I do the arrow there because why not, okay? And then look, they both intersect. That looks promising. Would this be like the center of our circle? Let's look at what the radii are, and if they're the same. So we're gonna look from here. These two, we know they're the same because we got same x distance, same y distance. So we have the same, we have same x, we have same y, we have same r. So r is equal to this r, good. And then what about for this guy, for point number 3, when we draw this line to the center? Well, we can't directly say that the relationship between here and here, but we can say that this length is equal to this length for the same reasoning. We have the same x, horizontal distance, quote unquote, and same vertical distance. Forgive me if I'm maybe emphasizing this part too much. Let me know if I don't like, if you want me to emphasize it more, like maybe just like explicitly write out the equation. Let me know if it's good that I'm doing this, if I should do more, or if I should do less of my emphasizing. But yeah, cool. Okay, so side note aside, since we know this line equals this line, and this line equals this line, we know the radii are, all these lengths are the same. So this is indeed the center of our circle. Nice. Now, perhaps we should look at this more algebraically. It's just more of a visualization here. Oh, let's just select everything. Just so we can start over. Look at it a little bit differently. And we don't really need that line anymore. Okay, beautiful. So, visual. And now, algebraic. Okay. So, for this, we're going to have a very similar start point. We see we have some distance x, total distance 2x, but now let's actually say some sort of distance between 2 and 3. And remember that the labeling just arbitrary, so any point could be 2 or 3. So let's say 1, 2, 3. You know, when you actually are just given 3 points, it's just to make it easier for us to deal with right now. We're gonna have some distance h. H could be negative. If h is negative, we're gonna be going this way. But for now, let h, if positive, be this direction. And then we're gonna have some b. Let b be positive, so it's going in away from the center, away from our distance between 1 and 2. If it's negative, it'll be going into this, or going in to this direction. Okay. And then we're gonna have, we see we have our points here in the center that allow for us to have a circle given points 1 and 2. We're going to call this vertical distance y. We don't know what y is. We are given, so let's write this down actually. So our fixed values given some 3-point configuration, they're going to be x, so our distance essentially between points 1 and 2, b, which is our horizontal distance from points 2 and 3, and h, which is our vertical distance from points 2 and 3. Okay, what we don't know, or our, you know what, let's write that, what we don't know, okay. What we don't know. We don't know what r yet is, our radius, and we don't know what our y yet is. So let's figure that out. But just a little side note on y. Y can be anything, right? Because we're just saying y is just some vertical distance along this green line. So can be toggled. So we're gonna toggle it and see if we can get something that we can, if it's possible for us to get our r. You're gonna see what I mean in a second. I just have to write down the actual equations. So r, we'll call it Pythagoras again. Pythagoras! Beautiful. Okay. So Pythagoras, if we're looking at points 1 and 2 to wherever our center is, what is r going to be? R squared going to be? R squared is going to be x squared plus y squared. But r squared, because we want the radius to be the same, we want them all to share the same r. R squared is also x, in this case, plus b, because it's moving towards the center, so it's b plus x. So from here to here, horizontally, b plus x squared plus y, wherever our y position is, where here y is equal to 0, minus h, right? Because since the point starts here, not sure why I said it that way, because point 3 starts here, we're going to be taking away our h value from our y to actually find the vertical distance, of this triangle. Yeah, so that would be our b value, y minus h squared. Okay, so let's equate the two, because they're supposed to be the same. We want them to be the same at least. So x squared plus y squared equals x plus b squared plus y minus h squared. And let's expand. X squared plus y squared equals x squared plus 2bx plus b squared plus y squared minus 2yh plus h squared. Okay. Both sides we got x, both sides we got y squared. So 0 is equal to 2bx minus 2yh plus b squared plus h squared. From what we said prior, these are our fixed values. So what's fixed? We can't change what h is. We can't change what b is. we can't change what x is. So this whole term is a constant. So what can change? How can we make sure this equality is always true? We always want 2bx minus 2yh plus b squared plus h squared to equal 0. Well, conveniently, we got this term right here. Right, this negative term. So we have this being positive always, this potentially being negative, and this having the capacity to be positive or negative. So because y we haven't given it a value, we can just give it some value so that this equality is true. And in this case, if we just rearrange everything, that would be h squared plus 2xb plus b squared all over 2h. Cool. So, some things to keep in mind. Let's say these 3 points were collinear, meaning h was 0. Then what would y be? Y would be some number over 0. So essentially, you're not gonna get the radius or the y, the value of y has to essentially be like infinity. Right, if it's collinear. So you're not really gonna have a actual center of your circle. And what if h and b were equal to 0? Well, in that case, if h was 0 and b was 0, so let's say this was actually also 0.3, then y could be anything, once again, because y could be anything on that green line. So you could have deduced that visually or just from this equation. It's interesting to see how the equation reacts to these values being what we don't expect. So if h and b were 0, then y would be 0 over 0. So essentially anything. 0 over 0, there isn't really a given value for that. So it's just interesting how the algebra reacts to it. Maybe let's keep that. Okay. Now to get a visual as to how the placement of the third point impacts where the center of the circle is. I'll see y'all next time. Just bye.